Okay, you wanted to know about photons. We talked about electrons, now we're talking about photons. This little thing is titled blackbody radiation. What kind of a weird thing is that? Blackbody. What is a blackbody? Well, let's see. A blackbody refers to an object or system which absorbs all radiation. So if something is black, it absorbs all the light. That's why it looks black. And this is important because it re-radiates energy, but it's not reflecting energy. It re-radiates what it's absorbing. This is only important because this is how we try to figure out what the radiant energy is dependent on the frequency of that energy. Here's a comparison between classical and quantum. So, number of modes per unit frequency per unit volume. Per unit volume. Okay, let's talk about this first thing. Per unit volume, that's where the 8 pi comes from. There's the 8 pi in both of those. Then there's it looks like a V, but it's actually the letter nu, the Greek letter nu, and this is standing for frequency. Why didn't they just put F there for frequency? Well, this is physics, so they don't necessarily do that. Then C down here is the speed of light. Why is the speed of light in here? Well, it's electromagnetic radiation, so it travels at the speed of light. So there's a relationship between the speed of light and the energy of these frequency modes. So in this column, everything is the same. Here's the probability of occupying the modes. Equal for all modes. That means all modes of the frequency can exist. And the average energy is kT. K is Boltzmann's constant, which relates energy to the capital letter T, which is the Kelvin temperature. Why is this one so complicated? Well, this one is used to come up with something that actually works in nature. This doesn't work in nature because as the frequency goes up, speed of light stays the same, but as frequency goes up, in other words, you heat the temperature up and the frequency goes up, the energy is going to skyrocket indefinitely. Eventually, it's going to go to infinity, which that doesn't make any sense. That's not going to happen. So let's look at this experimental curve. Here's the classical relationship between the visible light and 5,000 Kelvin. Man, that is really 5,000 Kelvin. That is really hot. So once it gets to 5,000 Kelvin, you can start actually seeing the radiation coming off of it. It has to be a really hot stove. The Planck formula makes it look like this. So it goes down. Well, let's see. Am I making sense of this? There's the radiation. Where's the frequency? Wavelength in nanometers. Okay. So nanometers is very small wavelength. Here's the visible light. And here's the non-visible light, that gets into ultraviolet light. Then this thing comes up here. This is what the classical formula comes up with, and it goes into infinity at the ultraviolet region, which is what they call the ultraviolet catastrophe. So, how can we understand this so it makes some more sense? Let's go down to this thing. I wonder what this is. Comments on the development of Rayleigh chains. Whoa, this is a bunch of stuff here. I saw this in another reference that I was looking at. This shows how you come up with that uh, particular relationship. Wavelength plot. Whoa, I think I better go back on this and go back once more. Let's try and make sense of these two. So on the next installment here, I will jot these things out in the, what am I trying to say, the 3D paint that I was using before, and write up these numbers and see if we can make more sense of that. This just doesn't seem like it's going to be easy to understand. So that's, if we can understand this thing, then we'll understand what the photon is in terms of math.